Any questions?
Not specifically.
Okay, then let's start talking about today's lab, mass spectrometry. I'm going to do a share.
Great.
And I'm going to be going back and forth between my book and what I'm writing and the lab. So here's the lab. The lab notebook is something you probably want to have out right now. And at the title, put mass spectrometry. And for the introduction, let's talk about the introduction, okay? So I'm going to switch my screen. And let's see, I need to do a little work on my Elmo here and rotate things. There we go. So for the introduction, we're going to learn about mass spectrometry. And for elements, it's used to determine their mass and percent abundance. And so really we're talking about isotopes there. So isotopes are something that hopefully you've read about. They are different atoms of the same element and they differ by mass. We're going to use mass spectrometry, MS, to make hypotheses, and we're going to test them. So that's your introduction. There's a little bit more, and that little bit more we're going to talk about right now. So to talk about that right now, I'm going to have to bring out my book and show you an image from the book on page 63. All right, so here's my book, page 63, and this is a cartoon of a mass spectrometer. So anytime I see an image that's hand-drawn and colored, I call it a cartoon. I'm going to zoom in on this just a little bit. I don't want to zoom in too much because I want you to be able to see certain things. I would like you to be able to see the cartoon of the mass spectrometer. I'd like you to see this spectrum or plot. And I'd like you to be able to read this as necessary. So let me describe the portions of the mass spectrometer to you. This is the gas inlet. This is the place where you insert your sample and you make sure that the sample is gaseous. So we make gaseous hydrogen, gaseous helium, gaseous oxygen, even gaseous gold. And so this is a pretty hot spot right here if you want to make gaseous gold. Now here you see we have a repeller plate that has a positive charge. Now gaseous gold and all of these samples that are inserted into the instrument, they're neutral, they have no charge. So they're not attracted to this repeller plate and they're not repelled by it. But the gas particles will make through that little hole there. And the gas particles here are going to enter this space where there's an electron gun, which shoots electrons at the particles. And here we have an electron trap to capture those electrons that are being shot at the particles. Well, it is possible for a particle to have an electron removed because it gets hit by an electron. So let me draw that for you with the electron gun and a particle. So here's your gun. And it's shooting electrons. And let's say this is your helium atom, which has two
I can't see all your drawing.
Oh, thank you. Sorry about that. So here's your gun, and here's the trap below. And here's your 2 electrons on the helium. What can happen is one of these electrons gets knocked off by that electron. So here's your gun. Here's your trap. And here's your helium. Now this helium has 2 protons in it and 2 neutrons in it. So in the nucleus, it's got a +2 charge. Outside, it's got a -2 charge. You add it all together, it's a 0 charge. Now what's going to happen afterwards, when you knock one of those electrons off, is that the 2 electrons are going to end up going to the trap, and they're trapped. But if you look at this helium, it now has 2 protons, 1 electron, and therefore it's got a +1 charge. That's called a cation. So that's what happens with your electron gun is you knock an electron off of an atom or a particle. It doesn't have to be an atom, it could be a compound. Like you could put H2O in this and you could knock an electron off. And if you knock 1 electron off, you're going to get a +1 charge. Now, the way we draw this helium atom with a +1 charge is this way. Helium with a +1 charge. Pretty simple. What do you think we would draw if it had a +2 charge?
2 plus.
2 plus. Okay, and cation means positively charged. So I'm going to go back to the cartoon. And I want you to think about, I'm going to zoom in again and you'll remind me again to zoom out, right?
Sure.
Thank you. Okay. So you see this part of the gun is ionization. We are making a cation. Now, cations are positively charged, and this repeller plate is positively charged. So what it will do is it will repel that cation, forcing it to go to the right. Now here you see this acceleration section. All of these plates have a negative charge, which attract cations. So that cation is going to be attracted to these plates. What they don't show you is that most of these cations are going to hit the plates, get an electron, and just become a neutral atom again. Some of them, however, will be accelerated and they'll make it all the way through these plates. And because it's being accelerated, it will be going at a very fast speed. The speed depends on basically 2 things. The charge on the cation, which is +1, and the mass of the cation. So it will be accelerated to a certain velocity. And all of these ions in the mass spectrometer are only a +1 charge. So the real difference in their velocity is going to be due to their mass. And usually the smaller masses go faster, the bigger masses go slower. So if you take a look here, you can see that we have these 3 lines. They're using neon as an example. And you'll notice that there's a magnet here, the deflection part of the instrument. Turns out that you can change the flight path of an ion with a magnet. And depending on the size of the magnet, you can change the flight path a different amount. So you can fine tune this magnet so a particular mass to charge ratio, in this case, the mass is 21, the charge is +1, so the mass charge ratio is 21. And that's really convenient when you have a +1 cation. The mass is the mass to charge ratio. So the mass to charge ratio on this neon is +21. On this neon, it's +22. On this neon, it's +20. And each of these will have a different flight path because of the magnet. Now, here's the detector. we can fine tune this magnet so a particular isotope or cation of an isotope hits the detector and none of the others do. So this ion does not hit the deflector or detector, so it's not detected. This one does not hit the detector, so it's not detected. You can see that with a magnet, it's easier to change the flight path of a smaller isotope, 20, rather than a larger one, 22. And I think that makes sense, right? If you want to change the direction of something speeding by you, it's going to be easy for you to change the direction of a cat running by you, but it's going to be hard for you to change the direction of a car. Those, of course, are extremes, but here, it even works for this here. So how do we get the mass of each isotope? Well, you tune the magnet so only a particular mass to charge ratio comes through. And if that's what comes through, you now know the mass of that isotope. How do you find out how many 21s there are, how many 22s, and how many 20s there are relative to one another in a sample? And the answer is simple. Turn your magnet so only the 22s come through for 10 seconds and count them. Turn the magnet on so only the 21s come through for 10 seconds and count them. Turn on the magnet so only the 20s get through to the detector for 10 seconds and count them. So the idea is there, we turn on the detector for each different isotope for the same amount of time, and you count how many isotopes hit. And then you compare those results. And that's what we see over here on the right in this graph. You can see that they have the percentages right here where roughly the 20 is 90%, the 21 is like 4%, and the 22 is like 6%, something like that. Now, this isn't the actual output of the mass spectrometer. Let me show you what the actual output would look like. So here I have my paper, and I'm going to draw what the actual output would look like. So this axis is going to be intensity. This is going to be mass to charge ratio, and we're going to have 20, 21, and 22. The way a mass spectrometer works, and I'm going to have to move this up just a little bit, and I'm going to move it over to the right so you can still see this. The way this works is that the peak that is the tallest means it's the isotope that you have the most of. That's automatically assigned exactly 100. And then the other peaks are drawn relative to that 100. So you might have 100, 5, and 10. Now notice these numbers don't add up to 100% because they don't represent 100%. 100 just means that that is the biggest peak. And this means that this is 1/10 the size of the biggest peak. And this is 1/20th the size of the biggest peak. So these lines here are called peaks. You could also call them signals. So again, we can get the relative amounts of each isotope, and we can also determine the mass because we adjust the magnet for a particular mass. Okay, so that's how a mass spectrometer works.
What you just drew there is not the same as the analysis in the books, the graph next to it.
No, this is what you actually get from a mass spectrometer. They don't give you percentages. You have to turn that into percentages.
Well, and that's what I'm wondering. Did they take, these approximate numbers and put them all over the biggest peak in order to find the percentage here?
If you want to know how to find the percentage, which is an excellent question, let me show you. So let's say you get something like this. Now I'm going to have to zoom out. So we're going to pretend that we get a spectrum that looks like this. 20, 21, and 22. I'm inventing these numbers here. This is 100, this is 5, and this is 10. Okay.
Mhm.
So how do we turn these into percentages? Well, percentage is equal to part over whole times 100%. So if we want to take this 100 and turn that into a percentage, that percentage would be equal to 100 over 100 plus 5 plus 10
Plus 10.
times 100%.
So I guess the better question would have been to ask, what is the measurement of those 115?
It's
What
how
is the
many,
measurement?
it's how many isotopes they get.
Okay,
So
it's a
let's say
number of
that-
isotopes.
Let's say
Okay.
here you get 5,622. Okay, that's how many you get. Rather than call it 5,622, they say 100. Now this one, let's say you get 56. Instead of calling it, or 562. Instead of calling it 562, it's called 10 because this is 1/10 of that. And let's say this one is, I'm stretching it here, 281. Instead of calling it 281, you call it 5. So the biggest peak is automatically assigned exactly 100. And the rest are relative to that
Okay.
one. You see, if I drew this thing and I made this 5,000, and that's 2,500, and this is 2,000, and this is 1,000, and this is 500, and this is 50. Here's how these numbers would look over here. So 5,622 would look like this. 562 would look like this, and 5 would look like this. Do you see how 5,622, 281, and 5,062, they look the same as this?
Yes.
But
So if you were
instead of
you were
using
to
the raw
lay-
data-
sorry.
instead of using the raw data, you just say that's 100, and then you figure out how big that is compared to that being 100.
Okay.
Now, this is the stuff that the mass spectrometer reports. And the reason why it reports this instead of this number is because this number here I gave you, 5,622, is far lower than what they get. It might be more like 5,622,000.
Mhm.
And it's not 10 seconds, it's like less than a second. It's just amazing. So they don't want to deal with these big numbers, so they make that 100. So let's see what this percentage is of this big peak here. We get 100 divided by 115 and then times 100. And so this would be 86.9 or 87.0. This one would be 5 over 115 times 100. And this one would be 10 over 115 times 100. And respectively, this would be 8.7%. And this one would be 4.3%. And when you add these values up together, you're going to get 100. So if we take a look back at the book, you can see very well, especially if I zoom in on this, how this value here might very well be 87 point, what do I have? 87.0%. And this might very well be a 4 point whatever percent. This might very well be 8.7%. Okay, so that's how they do that. And that's actually part of this lab. We're going to be doing some of that kind of stuff. So it's a great question. So does that kind of answer why this is different than what I drew? So that's
Yes,
what's in the
yeah,
book.
it does.
And
does.
here's what I drew. This is the real type of data that we get.
That's cool. It helped me understand. I appreciate it.
Okay, so the other things that you might want to put in your introduction based on what we just saw is that you might say that the mass spectrometer can be fine-tuned to detect specific masses with a charge of +1. And then you could also write, and if you tune it for each mass for the same amount of time, you're going to get the relative amounts of each isotope. And that's basically your introduction. If there is one more thing I would put in my introduction, it would be generally what a mass spectrum looks like. But before we do that, let's take a look at a mass spectrum from a source, a real source. We're going to do that in a bit, but I also want to go back to the lab. So I'm going to switch my share back to the lab. And you can see that we have the stuff that we're supposed to submit. We'll come back to that. I've got this little intro you can read about mass spectrometry. I got some background. Here's one of the sites we're going to go to, this www.sysweb.com. And this place, we'll see how we use it in a little bit. This is just your introduction to it and what you expect to see. And some more background. No safety issues. And after the safety issue, we normally have a procedure section, then a data section, then a calculation section, then a result section. This should actually read procedure, data, calculation, result all together. And we're going to do that for each step. So notice it says, do each of the following step by step, do not look ahead. So we're going to do this step one together. And this is stuff that, you know, after you write your safety, so write your safety in your lab notebook right after your introduction, say, there are no safety issues in this lab. Now, I want to go ahead and proceed. So if you haven't finished your introduction, leave a little space there for it to finish it off.
That's what I did.
Go ahead and write your safety section. And when you're done with that, give me a thumbs up.
Where's my reactions?
Okay, great. Now we're going to go to webelements.com and link to bromine. Scroll down till you find the bromine isotopes and a plot. Find the link that says more isotope and NMR data, open it up, and then copy down the table and the plot. Okay, so I'm going to do that right now. This is webelements.com. And here's bromine over here. So I'm going to link to that. So you see how easy it is to link to bromine. And now what I'm going to do is I'm going to scroll down and we are going to find physical properties, heat properties, electronegativities, atom sizes, abundances in substances, biological data, and then all of a sudden there's bromine isotopes and there's a bromine isotope pattern right here. Can you see that?
Yes.
If we scroll down a little more, do you see where it says more isotope and NMR data? That's where we actually want to go because we're going to see that plot again, but we're going to see the numbers behind the plot. So I want to bring your attention to this table above, first of all. Do you see how it says isotope 79 bromine and 81 bromine? This is your standard type symbol for the isotopes. An additional piece of information that we often write is a 35 underneath the 79 and a 35 underneath the 81. And just a quick heads up on what that means. because I don't know if you've watched the lectures or not. If we write 79 BR, that means 7935 BR. Here's your BR. There's the 35, and this is 79.90. So if we round 79.90 to the ones, we get 80, and that doesn't say 80. There's an 81 BR, and that means 8135 BR. And there's no 81 on the BR symbol either. So these are isotopes of bromine. And these are different ways of writing the isotopes. Another way is writing the isotope this way. So what does each one of these things mean? Well, I'm going to write this very large. And this is the number of nucleons. So that means protons plus neutrons. How many protons and neutrons it has total. This is the number of protons. So if it has 35 protons and 79 nucleons, we can do a little subtraction here. And we got that it's got 44 neutrons. Now, this is the standard method of writing the symbol of an isotope. This is called mass number. This is called atomic number. And this is the symbol. So the mass number is the number of protons and neutrons. So it's either 1, 2, 3, 4, 5. Z is the atomic number. And in an elemental symbol, you find Z right there at the top. That's how many protons that element has, 35. Okay, so I'm going to go ahead and go back to the other share, this one right here, so that we understand a little bit more about what's going on here. So do you see the mass to charge ratio? Z is the charge. It's a different Z than this Z that I wrote here. In this case, we're talking about cations with a +1 charge. And the other thing I want to tell you is that each nucleon weighs 1.00. So if you have a bromine 79 with 79 nucleons, it weighs 79.0. And what's 79.0 divided by 1? 79.0. For the other bromine isotope, what's 81 divided by 1? 81. So that's why we have two signals here, or peaks, at 79 and 81 for each of these two isotopes. The next part of the table actually tells you the mass of each isotope. And you can see if we round to the ones, we get 79 and we get 81. Here you see the natural abundance, which is 50.69% and 49.31%. Go ahead.
I sneeze.
Oh, I'm sorry. I thought there was a question. My apologies. So here, if you take a look at the graph here, can you see how the first peak at 79 is just a skosh taller than the 81 peak? Just a skosh. So yes. Notice the numbers above those peaks in red and in blue. The red is the intensity of each. Now notice they call it relative intensity percentage. It shouldn't be in percentage, it's just relative intensity. Percentages should add up to 100. 197.28 don't add up to 100.
Indeed.
So they are just relative intensities. Relative to what? Relative to calling the largest peak 100. Exactly. So how many significant figures in the 100? Infinite. And you see those numbers 50.69 and 49.31? They are the percentages based on the intensities. Let's take a look at that very quickly here, just for practice. So I'm going to do a share screen that switches back to my paper. So one of the peaks is 100, the other's 97.28. Let's find out what this percentage is going to be. Well, it's going to be 100 over 100 plus 97.28 times 100%. And that should get us the percentage. And here, we're going to end up with actually 5 significant figures. And I'm going to show you why it's 5 significant figures. This has infinity significant figures. This has infinity. This is good to the 100th. This is not good to here. It's actually good to the infinitieth. So when we add these together, it's good to the 100th. Now we're doing division, infinity, infinity, and 5. We get 5 significant figures. So let's see what we get. We get 50.689%. And if we do it for the 97.28, here we would only get 4 significant figures. We get 49.31%. So those are the percentages we calculated based on the 197.28. I'm going to change my share back to the web page, and let's see what numbers they get. They get 50.69. They didn't round that correctly. And they got 49.31, which is what we got. So that's where those blue numbers come from. You actually have to calculate them. And you'll notice in the little paragraph below, it says isotope abundances of bromine in the above, the most intense ion is set to 100. Since this corresponds to the best to the output from a mass spectrometer. This is not to be confused with the relative percent isotope abundances, which equals 100% for all of the naturally occurring isotopes. So I don't like to use the intense is 100%. I like to say it's just a relative intensity. It makes more sense not to conflate percentage. Percentages should not add up to over 100.
Got it.
Okay, so there's your isotope. Any questions so far? So we're still on part 1, step 1. Let's go back to the lab. And this is what we just talked about, calculating percentages. Now, step 1, go to the mass spectrum simulator, type bromine into the simulator, and obtain the mass spectrum of bromine. Report the data table, draw the spectrum, and calculate the percentage of each isotope based on its intensity in the simulator. So let's take a look at that together. We can write this in your lab notebook right away. There's no need to mess around. So this is your, oops, I got to get rid of that. This is your simulator here. And can you see how it says chemical formula? I type in bromine. And when I hit return, I get this data table, which says there is a peak at 79 AMU or U, and that's the 100 peak, and there's one at 81, which is 97.5. So I want you to write that table down. let me show you how it might look in your book, if you don't mind.
No, I don't mind.
So I'm going to write data table. And then I'm going to write intensity. You can't see this yet, but you'll see it in just a moment. And you're going to look, we're going to have mass. All right. And here you can see the plot below. We can duplicate that from the data. It's really easy to do. Notice they have M over E. That E really means the charge. So now I'm going to do a switch screen. And this is the rest of step one. Your data table, we're going to have a mass of 79 with an intensity of 100 and a mass of 81 with an intensity of 97.5. So that's your data table. Here we're going to have intensity. Here we're going to have mass to charge. We're going to have a 79 and an 81. Notice I'm not making any attempt to start at 0. No attempt. I just want to make sure 79 and 81 are on there. And here, that's going to be 100. And this is going to be 97.5. You'll also notice I did not make any attempt to make sure that the 97.5 was precisely 97.5 compared to the 100. I made it look like it should be lower than that one, and I call it 97.5. So you don't need to take out the ruler and, measure these things. So this is the answer to that question of print the data table in your lab notebook and the spectrum. Any questions there?
No.
Okay. Then we're going to go back and I'm going to do another share screen where we're going to go back to my browser, and I'm going to go back to here it says, draw the spectrum, calculate the percentage of each isotope based on its intensity in the simulator. And then finally, comment on the calculated percentages from the simulator compared to those found on webelements.com. So I'm going to do another share. And let's calculate the percentages of each of these peaks. So for the 79 peak, we're going to say that the percentage is going to be 100 over 197.5 times 100%. 197.5 is 100 plus 97.5. This has 4 significant figures. Let's see what we get. I get 50.63%. And for the 81%, we have 97.5 over 197.5 times 100%. And here we only get 3 significant figures. So what's your answer there? When you get it, just give me a thumbs up. Okay, I get 49.4%. I'm willing to bet that agrees with what you got. Okay, if we compare,
Pretty simple.
Pardon me?
Pretty simple
Yeah.
calculation there. Yep.
We compare that to Webb Elements where we got 50.63% and 40, I think it's on the back of this paper, so I need to flip this over. We got 50.689% and 49.31. So 50.689% and 49.31%. How do these compare? Well, I would say the first numbers match, the second number matches, the third number matches, and the fourth is pretty close, 3 and an 8. Here, first number matches, second number matches, third match, a third, pretty darn close. So my comment would be that, you know what? They're pretty close to one another. But the reason they're not is because of the intensity. So this is from the simulator, and this is from Webb Elements. The intensity in Webb Elements was 197.28. That's why they don't come out to be the same. Are you with me there?
Yes.
So my comment would say, you know what? They're really darn close. The reason they're not precisely the same is because the intensity of the 81 peak differed slightly. And you're done with step one. Now we get into the fun part, because you have to be okay with making a hypothesis that you don't know if it's right or if it's wrong. Because when you make a hypothesis based on your best attempt at getting it right. But the reason you don't know if it's right is because you're making a guess. And you don't not make a guess because you're afraid of getting it wrong. Rather, you make the guess so that you know how to test it. And then after you test it, you analyze whether you got it right or wrong. And then you move forward. If you got it wrong, you make adjustments. If you got it right, you still may make adjustments. So let's have some fun with this and let's make a hypothesis. So I'm going to go back to my web browser. And step 2, trying to move my participants list over so I can see what is red here. Okay, there are 2 isotopes of boron, boron 10 and boron 11. The atomic weight of boron is 10.81 AMU. So that's the average. Based on this information, draw a qualitative plot of the mass spectrum of boron. Remember to make the largest peak 100 and draw the other peak proportionally shorter based on your intuitive guess based on the information provided. Take a photo of your hypothesis. So this is something you got to do with blank space following. You're going to submit that as one of your photos. So here's what I want you to think about. This is to help you out. Imagine boron 10 and boron 11. So boron 10 has 10 nucleons. How much does it weigh? And the answer is, since each nucleon weighs 1.00, 10 times 1.00 is 10.0. So boron 10 weighs 10 AMU. And boron 11, which has 11 nucleons, weighs 11.0 AMU, 3 significant figures. So do you see that number at the top? Not only is it the number of nucleons, which is something you count, but because each nucleon weighs 1, it's also the mass. That's why they call it mass number. really, it's not the mass number, it's how many particles. But because each particle weighs 1, it's also the mass. Capiche?
Mhm.
Okay. Now imagine 50% of the boron isotopes are boron 10, and 50 of them, 50%, are boron 11. What would the average mass be?
10.5.
10.5. Oh, but it's not, it's 10.8. So I want you to imagine that there were 9 boron 11s to every 1 boron 10. What would the average be? Closer to 10 or 11?
Say that again. There was a
1
glitch.
boron 10 and 10 boron 11s. What would the
It would
average
be far nearly 11.
And great. And if there were 10 boron 10s and 1 boron 11, what would the average be?
Nearly 10.
Nearly 10. So those are perfect answers. I'm not asking for actual numerical answers. So here, take a look at the atomic weight of boron. What is there more of? Boron 10 or boron 11?
11. So that's my hypothesis, correct?
That's your hypothesis. So you're going to draw a spectrum that reflects that. The largest peak will be at 11. And intuitively, you want to draw the 10 peak.
So you want us to draw a hypothetical
Yes.
hypothesis one. Okay.
Yeah. So here you're going to write, let me show you what I'm expecting. Okay.
Mm-hmm.
I'm going to do a new share. I'm expecting you to draw something that looks like this. Boron plot. We'll just call it the plot. Hypothesis. Here we're going to put intensity. And this is going to be 100. And there are 2 isotopes, one at 10 and one at 11. And we're going to put mass over Z. And now you draw the peaks in. Which one are you going to make 100? 10 or 11?
11.
11.
How big are you going to make 10?
Slightly less.
Knowing that the average is 10.8. So I'm going to draw some peaks in here. Would you draw it this tall? Would you draw it this tall? Would you draw it this tall? You know, how tall would you draw it? That's what I'm asking you to do. And go ahead and draw it. And then once you have it drawn in your lab notebook, take a picture. Save it in your phone because you need to send that. Isn't this kind of got your stomach in butterflies because you're drawing something that you're making a guess and it could be wrong, it could be right, you don't know?
Feels like a test.
It's science. But see, you're not being graded here on whether or not you're right or wrong. You're being graded on whether or not you have a hypothesis that we can compare to the real thing and see if you were right or wrong. So you're getting graded on whether or not you're willing to take that leap and make a guess, not the guess itself. What could be better than that? You're being graded on just trying. Yeah, that should not be a heavy sigh. That should be like, what? You mean I can screw this up and still get it right? Yes. So I'm going to show you another one here. Here's my 11. Here's my 10, and maybe this is what you have. So based on what I've drawn here, we're going to now take a look at the reality, and then we'll comment on this. So I'm going to switch my screen back to the browser. I'm going to go to the distributor, and here I'm going to type just the letter B, enter, and let's see what we get. Oh, look at that. 10 is 24.7 and 100. And take a look at that spectrum. So let's analyze this spectrum that I have on top. I'm going to do a switch screen. So let's analyze this top one. Number one, I would say I had a peak at 10 and 11, and so does the real spectrum. So we nailed it. Are you with me or not? Are you with me or not?
Yes.
I said peak 11 would be the 100 intensity, and in the real spectrum, peak 11 did have the 100 intensity. Nailed it. My 10 was not quite halfway. It was like a quarter of the way the size of the 11. And if we look at these real spectrum, the 10 was about a quarter of the size of the 11. So I feel I did a pretty good job. Actually, my 10 is not really about a quarter. It's like 0.2, but pretty close, correct? Let's analyze this one down below. Now, this one down below, I imagine you're looking at and you're thinking like, what an utter failure. But let's go through it point by point compared to the real spectrum. We predicted a peak at 10 and 11. Peaks at 10 and 11. Check. We said that the 11 peak would be the 100 intensity. Check. And then we said that the 10 peak would be over half the size of the 11. And that's where we kind of blew it. So this spectrum we have at the bottom, did we do a pretty good job? You're supposed to say yes, we did. The only thing we didn't consider was how close 10.8 was to 11, meaning that 11 should be a lot larger than 10. That's all. Capiche?
Yeah.
You okay with that, Darlie?
Yeah, I am. Sorry, I couldn't get unmuted.
That's all right. This is something we have to be able to do in science. We have to be willing to be wrong, willing to test ourselves, and willing to analyze what we did and then try to make improvements from that. All right? Okay. Now, I could have you do the same thing again for boron, but I didn't do that. I'm going to go back to the lab. And I'm going to go to the lab write-up itself here. Okay, so we just did step 2. Compare your hypothesis with the accepted result. What did you do well and not so well? You're also supposed to report the data table and the plot. Now, what you might want to do if you haven't written that into your lab notebook yet, you're supposed to have already drawn your hypothesis, but if you have not written the data table and not drawn the plot and not written your comparison, leave space for that. And let's go on to step 3. Because step 3 is where it gets really interesting. Okay, so there are 7 elements that are found as diatomic molecules. That is, 2 atoms are bonded together and behave as a single particle. The 7 elements are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. If you put them all together, can you see how HON spells Han, and Cl is Col, and BRIF is Briff, Honkelbriff. One way to remember these 7 elements is the saying, have no fear of ice cold beer. H is hydrogen, N is nitrogen, F is fluorine, O is oxygen, I is iodine, C is chlorine, and B is bromine. So elemental bromine is actually Br2 and not Br. If we write just Br, we'd say atomic bromine, 1 atom of bromine, atomic bromine. But the element is Br2 because it's a Hunkelbrief. When elemental bromine is subjected to mass spectrometry, it is ionized but not fragmented. So what this means is that an electron is removed, but the 2 bromine atoms remain as 1 particle. They are not broken apart. They remain together, like co-joined twins, if you will. Predict the mass spectrum of Br2 based on the premise that each particle will have 2 bromines, so it weighs more, and that there are 2 isotopes of bromine, 79 and 81. And actually, I should rewrite this a little bit. I want you to make a guess as to the spectrum, but let's take a look at the spectrum. So I'm going to go to the distributor, and I'm going to type in Br, because I want you to know how many there are of each isotope, just so you have an idea. So take a look at the 2 isotopes. There's 79 and 81. 79 is 100 and 81 is 97.5. Actually, we already did this one, didn't we? So we know what those percentages are. So they're almost equal. So now this is the fun part. What would the spectrum of Br2 look like? And here you can see I'm trying to help you out here. It says, well, you could say that one of the bromines is a bromine 79 and the other bromine is also bromine 79. And together they weigh 158. So you expect a peak at 158. All right. Now, I have a question for both of you. How do you feel about talking with each other about your ideas? Are you okay with that?
I mean, I'm okay with it, but I am in the hospital right now getting chemo, so my nurse is kind of in and out.
Oh, okay. Well,
Yeah.
maybe your nurse can get in on this too.
Maybe.
She might, well, she'll say, oh yeah, I hated chemistry. But here's something that you can do if you want. You can talk over your ideas. In a face-to-face setting, we sit at these things called benches where there's 3 people to a bench. And during this lab, I make the students at the bench discuss their ideas and band together and come up with a single idea for all 3 students. And the reason we do that in the face-to-face setting is because no scientist works by themselves. You know, those TV movies where you see the mad scientists working by themselves, like Dr. Frankenstein or, you know, some mad scientist? That never happens. Scientists might work in a room by themselves, but then 2 seconds later, they're out in the hallway talking to their, lab colleague. And, they might be saying, can you tell me about this? What do you think? And, the lab colleague says, well, you know what? Here's my ideas on it. Or have you thought about this? Science happens in a community. It doesn't happen in a room by yourself. So go ahead and try and come up with a hypothesis and let me know when you have one drawn in your lab notebook. So you're going to give me like a thumbs up. Now, here's where I'm going to pause this because it might take you a little while.
So
Okay, so let's go back to making the hypothesis. Okay, so just a quick rewind. If there's two 79s and it turns into an ion with a +1 charge, we expect that this guy should weigh 79 plus 79, 158. But there's this other isotope, and maybe you could have two bromine 81s combined together, which would weigh 162. So we have a peak at 158 and one at 162. Now, because each bromine 79 is more likely than each bromine 81, it seems that two 79s would be more likely than two 81s, but only slightly more likely because we're looking at 100 versus 97.5. So we make the intensity of 158 100 and the intensity of 168 a little less than 100. And there's our hypothesis, and we can test it. Okay, now I'm going to back up just a little bit to try and help you with this idea here, Alice, that I think you might have a little bit of trouble with. Here's a bromine atom. This is a bromine 79 with 35 protons and 44 electrons. And there's 35 electrons here. Or, I'm sorry, I said that wrong. 35 protons and 44 neutrons. I'm going to pause this for just a second, and then I'll start it again. Okay, so this is a bromine 79, and it has 0 charge. Here's another bromine 79. And these guys are stuck together. So this guy overall has 70 electrons, 70 protons, and 88 neutrons. When you submit this to the mass spectrometer, you're going to see that guy right there, and an electron gets knocked off of it. When an electron gets knocked off of it, so let's say it gets knocked off of this one, and we only have 34 electrons now, and so only 69 electrons. Because you have one more proton than electrons, you got a +1 charge. This is the thing that goes to the detector. It doesn't get fragmented, does not get split apart. Does that kind of help you with that idea, Alice, of what's going on?
yes, it does.
Yeah,
Yeah.
you don't have to split it apart. Okay, so shall we test our hypothesis?
Yes.
Yeah, let's do it. I'm going to go back to the web browser, and I'm going to type into here BR2. Now, there's no way to do a subscript on this. So you just type B lowercase r and then 2 and a little drum roll. Let's see what we get. Hold on a second. Well, there's the 158. There's the 162.
And one in the middle.
And there's a 160. Where does that come from?
What the heck?
What the heck? Where does a 160 come from? Are there two bromine 80s? An 80 and an 80 makes a 160, right?
Mm-hmm.
Is that possible? Here's how we find out if bromine 80s are possible. Let's type in BR and see what we get. We type in BR and we get, nope, there's only 89s and 81s. There's no 80s. So back to that bromine with BR2. How do you get a 160? Have you guys ever heard this joke? It was a joke that was popular 30 years ago. Not really a joke, something to make you think. A man and his son get into a horrible auto accident. The father doesn't make it, but the son makes it to the emergency room, goes up to ER, and the doctor says, I can't operate on him. He's my son. So what's going on there? Father died in a car crash. Doctor says, I can't operate on him. He's my son. And no, it's not one of those broken families.
That's where I was going.
Me too.
The answer is the doctor is his mother.
Right.
So-
I knew I
If
heard
you
that
didn't-
before.
If you didn't think about that answer, it's because you're kind of genderist. Oh, women can't be doctors. You with me? So right
Or we're
here,
just raised in this society.
so right
Yeah.
here, what is the assumption we made about the pairs of isotopes?
That they're the same.
They're the same.
Yeah.
Do they have to be? I mean,
No.
does
Say
one
no.
isotope look at another isotope and say, no, you're the wrong isotope. I don't want to hang out with you.
That's
So-
why my brain was having an issue, because I was trying to pair what I literally drew a 79 and an 80 together. So
You should have,
an
yeah,
81.
and that must be what a 160 is, right?
Hmm.
It's
Yeah.
got to be a 79 and an 81. But let's think again. If there's a 79 and an 81, shouldn't that be less likely than a 79?
I would think so.
Yeah.
Less likely,
But
but
it's twice as big. What's going on?
good question.
So let's go back to web elements. Not web elements. Let's go back to the lab. You'll notice I give you a little explanation. And do you recognize this little green thing here with the P's?
Yes.
Yeah.
Mendelian genetics, and this is a Punnett square.
Mhm.
Do you see that uppercase G, lowercase g is 50%?
Hmm.
Right.
Big G is
So-
25%, and GG is a little g is 25%.
Yeah.
So this is based
Yeah,
on
so-
the idea that it's a 50-50 for each, right?
Right, but the dominant probability is what comes out as the visible.
We're not worried
portion.
about, we're not worried about
So-
phenotype. So I'm going to go to a different chair here, and I'm going to draw Tony's square. Okay, here's Tony's square. This is bromine 79 with an intensity of 100. This is bromine 81 with an intensity of 97.5. And I'm going to do the same over here, just like a Punnett square. Only this is Tony's square. So here, if you have a 79 and a 79, how much does it weigh? 158. If you have a 79 and an 81, how much does it weigh? 160. How much does an 81-79 weigh? 160. How much does an 81-81 weigh? 162. So this gives us all of the different masses. Are you with me there?
Yeah.
What is the likelihood of getting this guy with a 79-79? And the answer is we do 100 times 100 is 1,000. What's the likelihood of this guy? 9750. 100 times 97.5. Okay. And this one's going to be 9750, 97 times 100. And this one's going to be 97.5 times 97.5, which is like 9510. So this is kind of like the relative intensity of each of these, but we really don't want to do that. We want to figure out which one of these is going to be 100, if you will. You with me?
Mhm.
Now, for the mass to charge ratio, the relative probability is 1,000. For a mass to charge ratio, oh, I did this wrong. For a mass to charge ratio of 160, the relative probability, so these are probabilities. The relative probability, and 1, 2, I'm missing a 0 here. Do you see that?
Yeah.
The relative probability of a 1/6, oh, that should be 158. I screwed that up too. Of a 160 is going to be these two numbers added together. So what does that add up to?
Um, 320. 320.
19.5. These two.
Oh, sorry. Yeah.
I'm sorry. And the 162 is going to be 95.10. Now take a look at these numbers here, and I'm going to draw this 158, 160, and 162. Which one's going to be the tallest peak? 158, 160, or 162?
160.
Okay, and we know that's about 20,000, right?
Mm-hmm.
How big's the 158
Yeah.
going to look compared to that one?
Half.
About half. Better make that a little taller. How long is the 162 going to look compared to that?
A little smaller than the 158.
Yeah.
Now, let's go back to the web browser and take a look at that spectrum on the simulator. Does it look like the 160 is twice as big as the 158?
Kind of.
Yeah. Does it look like the 162 is shorter than the 158?
Yeah.
Slightly.
Let's look at the data. Does it look like the 158 is about half of the 160?
Yeah.
51.3, that's about half. Does it look like the 162 is about half of the 160? 48.8 is just about half of 100, right?
Yep.
Does it look like the 162 is just a skosh shorter than the 158?
Yes.
So this explains what's going on. I'm going to do another share here. And how might I turn this into those numbers we saw, 100, 48.8, and 51.3? I'm going to show you how to do it. You take this 10,000, divide by 19.5, and multiply by 100. You take this 19.5, divide by 19.5, and multiply by 100. And you take this 9510, divide by 19.5. You remember how the golden rule in algebra is what you do to one number, you got to do to the rest?
Mhm.
What am I doing to each of these numbers? I'm dividing by 19.5 and multiplying by 100. Can you see we don't need a calculator for this answer? It's 100.
Mhm.
That's the biggest peak. Let's use a calculator on this one. I get 51.3. And this should be percentage here. Let's see what we get on this one. I get 48.8. And I'm going to go back and do a different share where we can actually see the spectrum. And let's see what numbers they have. 51.3 and 48.8. So we need to use a Tony square to figure out a spectrum where you have two different isotopes for an element. You with me?
Yes.
But do we really need it? What I mean by that is, if we now know that there's a bromine 79 and there's a bromine 81, so I'm going to do another share. So this time we're not going to do any real calculations other than adding masses together. So we've got a bromine 79 and a bromine 81, correct? And this is 100 and this is a 97.5. Do we know we can have a 79-79? We do, right? Do we know we can have a 79-81? We do, don't we?
Yes, we do.
But we also know we could have an 81-79. And we could have an 81-81.
Correct.
So the idea here is that we have four possibilities, and since these are even, it's going to be about 25%, 25%, 25%, 25%. But this, you know, when we draw it, and I've seen this done before, so I want you to avoid it. You see how we have 25, 25, 25, 25? And there's two 160s. We don't want to do this. You see how I've drawn them all the same height and I've drawn two 160s? Don't do that. I've got a question for you. Do you think your mass spectrometer can see the difference between a 81-79 and a 79-81?
No way.
No way. So your mass spectrometer is going to take those two 25s, here's one and here's the other, add them together, and it's going to do that. Are you with me?
Yes.
Almost.
So wasn't that kind of cool? You come up with an idea. Alice had this idea that maybe we should put two different isotopes together, and that would have been a great idea to run with. But even when people do that, they tend to come up with this. Blah, blah, blah. They get shorter as you move along. And so even there's something to learn, isn't there? So what did we learn? We learned that, well, we don't want to be isotopist when we're talking about pairs. In other words, we don't want to say that an isotope has to be paired with another of the same isotope. They can be, but they can be paired with the other isotope. Capiche?
Isotopist.
You don't want to be isotopist. Okay.
Got it.
I think that's kind of funny.
Yeah, trying to refrain to be an ist of anything.
Yeah, you don't want to be an ist.
Got it.
And so also you need to consider not only every combination, but the order of the combination. 79, 81, 81, 79. That matters.
Right.
Okay. And so here, do you see that we didn't really do any calculations here? We just said, okay, this is going to be big, small, small.
Mm-hmm.
But we could also have calculated them. Okay. So this next part, you're on your own. I'm going to do a new share. Don't cringe. It's okay. It will be all right. Because, oh, I should say, how do we analyze what we did? Well, we say, well, we got the 158. We got the 162. We did have that the 158 would be slightly taller than the 162, and those are all the good things. So what do we put as the bad things? Well, we missed the 160. And we didn't realize that the 160 would actually be the most intensive peak. And we didn't realize, or we didn't, put as part of our hypothesis that an isotope could pair with a different isotope of the same element. And that's what you write. You learn. Okay.
Mhm.
So let's go back to the lab itself. And we've gone over, but I get pretty excited by this crap. You can see how I calculated the intensities here. I divided each one by 100 instead of just multiplying, and it works out the same. So now we apply what we learned. Use the simulator to get the mass spectrum of atomic chlorine. So Cl, not Cl2. Report the data table, and then make a guess as to what the spectrum will look like. And then calculate the spectrum. And then look it up and see how you did. So let's do the first part. Here's the spectrum of atomic chlorine. How many isotopes are there?
2,
2.
35 and 37.
35 and 37. Which one is bigger?
37.
35. Oh, I'm sorry. Which one has a bigger abundance?
35.
35.
By 3 times.
Because when you answered the question, which one's bigger, 37 is clearly bigger. And I didn't ask the question correctly. That's on me. Which one is most abundant? 35. And that's what I meant
35.
to ask. I'm sorry.
Yeah, that's okay.
So, yeah, but so many times, a teacher will ask a question and the student answers the question and the teacher goes, oh, that's not what I meant. As if you could read my mind. You know what I'm talking about? So at any rate,
Yeah.
here's what the spectrum looks
You're
like.
human.
So what's CL? Yeah, definitely. I'm more human than most people, in fact, if you base it on
Yeah, me
making
too.
mistakes. So what's CL2 going to look like? Think about it without doing calculations other than adding masses together, and then calculate it, and then type in CL2 and see how you did. Are you with me here?
Yes.
So I'm going to let you guys fly on your own and have at it. Thank you for attending. You can see that this is probably one of those lectures that you really want to come to.
No kidding.
All right.
Okay.
We'll see
Thank
you
you.
tomorrow. Today, I'm going to be working on Thursday's lab. Thursday's lab is going to be another one of these where the safety issues are that you don't want to poke your eye out with a pencil. That's pretty much the safety issue here. I don't want to poke my eye out with a pen, although I might want to. We're going to be looking at formulas of compounds and names of compounds. So that's going to be Thursday's lab. You don't want to miss that one. I'm going to try and get that posted today so you can do a little reading on it. All right,
That'd be
this
great.
one is due next Monday, so you've got plenty of time to work on it. And you guys are almost done.
Yes.
All right. Thank you for attending. I appreciate it.
Thanks.
I really do. I hate
Thanks for
talking.
having us.
Thanks,
Yeah, thank
Tony.
you.
All right. Bye-bye.
Bye.
Bye.